Assalamualaikum. We continue with the second part of the infrared spectroscopy, where we go for the different functional group for the different organic compounds. For the IR absorption from previous lesson, we know that the bond range affect the frequency of IR absorption, whereas when the S character, for example, single bond CsP3 and followed by the S character increase 50% for the C triple bond. So when the increased percent of S character, the wave number also will be increased. The higher percent of S character provide a stronger bond and the higher wave number is absorbed. This is the refreshment for the previous lesson, and now we see the first group of organic compound, which is alkane. Alkane is a saturated, which is C single bond C and CH bond. So the typical signal for C single bond C is band between 1360 to 1470, and this is the band for C single bond C, and CHsP3 is another things important for the alkane group, which is 2800 to 3000. This is the signal for CHsP3. Next, the absorption example for this molecule. As we can see, this is the signal for C single bond C. This one is for CHsP3. And same goes to this one. This is a C single bond C, and this one is CHsP3. Same, we can see for the cyclohexane also same, C single bond C, CHsP3. So next group will be alkene. Alkene, what is the difference is C double bond C and also CHsP2. CHsP2 is quite higher wave number, which is more than 3000, 3020 to 3018. Why? Because the CH is attached to the more strong bond, which is C double bond C. The substitute of aromatic and alkane can be out of plane bending vibration mode. So however, other peak also apparent in this region. So we can see how to differentiate between autometaphora in the fingerprint region. Different with one functional group is this frequency, and with the position of auto, this is the frequency. This one is meta and this one is para. For alkene, the typical signal will be the C single bond, C double bond C and CH. As I mentioned just now, C double bond C is 1620. Just now we can see C single bond C 13 something, and then now it become increase the wave number because the bonds range increase, and the CH also sp2 become more than 3000 to 3100. So this is two typical signal for alkene. Here we can see alkene 16 something and 3 more than 3000. sp3 is 3000 to 280. sp2 is more than 3000, 3150 to 3000. This is sp3, this one sp2, sp3, sp2, and this one is C double bond C. This one we can see the signal for CHsP2, and this one 16 is a C single bond, C double bond C. So in benzene ring, we can differentiate between auto, meta, para with the different frequency. Ortho is mono substitute, ortho substitute, di substitute, and meta, they have 2 region, and para is more higher. And C, single double bond C is 1500, 1600. That's for the alkene, because the aromatic also fall in the alkene group also. And in the region of fingerprint, we can know the region between 1667 to 2000 can shows us the presence of different aromatic system. This one is one mono substitute. The 1CH, this one 1500, 1600 in the benzene ring, and this one is mono substitutes. And ortho, this one is ortho 735 to 77. This is para, 8 something is para, and meta have to pick. That's how we can differentiate between ortho, meta, para in the benzene ring. This is mono substitutes, and this is C double bond C, and this one is RCH CH2. Okay, that's for alkene. Now it's come for alkyne. Alkyne is C triple bond 3, more higher with number because of the bond strength is more higher, and another CH is SP, also become more than 3200 to 3300. So the wave number of frequency keep on increasing because of the bond strength increase. This is the typical signal, as I mentioned just now. 3200 to 3300 is CHSP. This one is common in any organic compounds. Between 28550 to 3000 is for CHSP3, and C triple bond C is 2000 to 2200. That's for the alkene, alkyne, and alkene, and alkyne. Now go for the alcohol and ether. Alcohol and ether contain CO bond which fall in 1050 to 12705, and OH is 3200 to 3600 with a broad bond. This one is we can differentiate between CHSP, because CHSP is strong, this one is broad, although they are fall in the same region. So for alcohol, easily recognized, this is a broad band, and the presence of CO between 1050 1260. This is example for butanol, and this is easily recognized as I mentioned just now. And this also easily recognized, 3200, 3600, broad bands. And this one is for the CO. There are two typical, CO and OH, and same goes to this one, OH and CO, third degree compared to secondary 1075, third degree 1100, 1200. You see the frequency keep on increasing. Why? Because of the bonds range keep on increase. So next ether, the typical signal is only CO, which is fall in 1050, 1150, is compared with the alcohol. There's no OH broadband, so only here for ether, CO. For ether, typical signal, as I mentioned, this is a CO 1125. This is a typical signal. And next, the last part will be the carbonyl groups compounds, aldehyde and ketones, carboxylic acid, acid anhydride, ester, and amide. All these C double bond O fall in the region 1700 to 1850. The amide is more lower, 1680 sometimes. C, the aldehyde. So carbonyl group is the typical signal. 1720, 1740 is for C double bond C double bond O, and for the aldehyde they have a Fermi doublet for CHsP2. We can see a doublet here. So Fermi doublet for the CHsP2 shows the presence of aldehyde. And ketone, they have no Fermi doublet, so the typical signal is we can see the C double bond O and the sp3 in the normal region less than 3000. And C double bond O for the ketone, same, CHsP3 and C double bond O. And again the ketone, C double bond O, and ketone, C double bond O, and again the ketone. And now we go for the amide. Amide, we can see the carbonyl group is fall in the quite lower energy, 1640, 1680. When we see this one, they have can differentiate between primary amide and also secondary amide. Which is primary amide, the stretch occur 3200, 3500 as a doublet, while the secondary as a sharp singlet. This one doublet, so we know this is a primary amide. And this one we know the primary amide also. This one also we know this is a primary amide. Goes for the amine, same like amide. When doublet is so have a shows NH stretch NH2 as doublet 3200 to 3500 symmetrical and anti-symmetrical mode. So shows the deformation bond between 1590 1650. This is for amine, and this one is a strong to medium strength. This is primary amide, double bond. The secondary is single band. Same goes amide and amine, same. Nitrile group presents principal group in carbon nitrogen triple bond at 2100 to 2218. So we can see typical signal for this C triple bond N. Same region in the C triple bond C. So this usually much more intense than that in the alkyne. As I mentioned just now, the region is same in 2100 to 2218, but in the nitrile is more intense because of the presence of carbon and nitrogen. So we can see here the triple and bond at region 2250. Nitro group, two bands are seen, symmetric and asymmetric, at 1300 to 1380 and 1500 to 1570. In the medium or strong, this group is a strong resonance withdrawing group and self vulnerable to resonance effect because of resonance effect. So they have this stretch of the band, and the CO for the ester same with the 1735 to 1750. Display CO higher frequency than ether or alcohol at 1150 and 1250. C double bond O occur between 1700 to 1725 but have a broad band of OH because this is carboxylic acid between 2400 to 3500, medium or broad. For acid anhydride, they have a band between, they have two C double bond O band, 1740, 1770 to 1810 to 1840, and mixed modes of CO strength at 1000 to 1100. This is acid anhydride. This is acid halide. And dominant band C double bond O 1770 to 1820, and CCl at the fingerprint region 600 to 800. So important shape of the band. If you see U shape like this one is specifically for OH. We know that the OH is present. When you see sharp peak here, we know that C triple bond C bond appear, and V shape is for the NH bond for amine, and W shape is for NH for C primary amine, and small peak shoulder just above 3000. We know that C double bond C H or phenyl H sp2 present. This is the type of a shape of band that easily recognized in the FTIR. So there are different effects on the IR bands, whether conjugation and inductive effect. Conjugation, if a compound precipitate in the conjugation, higher energy is required rather than non-conjugated compound. So compared for this structure, although they have a same structure with a different position of C double bond O, and the value of C double bond O here 1715, and this one is 1684. Why? Because if compound, higher energy is required. When the higher energy is required, what happened to the wave number? Wave number will become lower. So compound A have conjugation, so absorb lower wave number than compound B. Easily conjugate here, that's why it have lower wave number, because when they involve in conjugation, the bond strength decrease. So inductive effect usually small unless coupled with a resonance contributor CH3 or Cl above. So that's why when CH3 Cl, the frequency is different. This one involved in the conjugation, so it weaken the bond, so the value is lower. This one is more strange, so the value is quite higher. That's all. Thank you.